very difficult time for me. Yeah, exactly. This time water also will come. So we are going to discuss about crystal field theory. Okay. So in crystal field theory, as I told you, the metal atom or ions do not form any formal bond with the ligands. Ligands come nearer to the metal atom and develop an electrostatic force of attraction if the ligand is negative and metal cation is positive, just like normal salts that we have seen. In normal salts, ions are held by electrostatic force of attractions. Or if the ligands are neutral, like ammonia, water, in that case, metal cation induces a polarity into the neutral molecules. By that way, they develop an ion and induced polar molecules. Or it may happen that it is a metal atom which is neutral and ligand is also neutral, just like the carbonyl complexes of nickel, iron, manganese, all these things. In that case, you will find they come nearer to each other and held by the van der Waals forces of attractions. This is the way they remain like this. And in that case, you will find, in case of transition metal, the d orbitals of the metal participate in this process. Process of the mutual attractions. So don't write it. So it is an interaction between metal ion and this is L-based ligand. So it can be monodentate, didentate, but these are all cation. So it is purely electrostatic force of attraction. Second, this and this. These are neutral ligand. So what will happen? We know any charged bodies induce a polarity. So it is going to induce a polarity into these neutral molecules. Again, they will be held by this ion induced polar interactions. Or very few cases you will find that these are neutral. Very few cases. So this is the way interaction develops and they surround the metal. And so now let us discuss. See, we know that there are 5 d orbitals. There are dxy, dyz, dzx, then dx square minus y square, and dz. Okay, now see how they are. This dxy, yz, zx, they lie along the plane. I'm not writing the plane. Okay, so it is like this. They lie along the plane. So if it is xy plane, then we call it dxy. If it is YZ plane, we will call it dyz. And if it is ZX plane, then we call it dzx. And these two orbitals are along the axis. Okay? See. Say it is Z. This is X. And this is Y. You know it very well. 3x square minus y square is this. Okay? And how does the dz looks like? Dz is like this. I should have drawn it here, but if I draw it, it may lead to some confusion. I'm drawing it separately. See this. And this is a circle. So, these are the 5 types of d orbitals. But the energy of all the d orbitals are same. Or what we will say in the spectroscopic languages, we call it the d orbitals are in degenerate state. Degenerate state. All right. Now, wait. My models are all broken now. See, can you see this one? Huh? It's white now, it's difficult to see. See here. So this is the, say this is the z-axis, this is the x-axis, and this is the y-axis. So in that case, what will happen? In this case, you will find if this is the z-axis, this is the x-axis, and this is the y-axis, dxy will be here. Dxy, this is xy plane. Okay? Then this is yz plane. The yz, dyz will be like this. This is zx plane. So this will be like this. And dx square minus y square will be along this axis. And dzx will be along the axis. Now, in the middle only you have metal. All right? Metal is here. How to screw it? Okay, you can see now all. Now, the ligands will, moment you want to make the complex, so you will put the metal in the, sorry, you will put the metal ion in the solution and you will put ligand. So initially what will happen? The ligand will come and surround the entire metal atom. Then the ligand will decide which way to approach the metal. Should it approach along the axis? See, in that case, they can approach along the axis. So in that case, ligand will come from this, say it is the X. So ligand will come from this side and back side. right side, left side, from top and the bottom. So ligands are approaching with, because they're having lone pair, and the d orbitals is also having electrons. So when they come nearer to each other, then the repulsion starts. When the repulsion starts, you'll find the energy of the dx square minus y square and dz square orbital will increase, but the dxy, dzx, these are all 45 degree to the ligands. So they do not come under direct repulsion. So in that case, their the energy decreases. By that, what happens? You find the 5 sets of their d orbitals now develop 2 types of energies. One with the high energies and one with the lower energies. So they do not now have the same energies, and they are being separated from each other. Means they are, in that, on the basis of energy, they split. Okay, so this is called crystal field splitting. So I'm going to show you the diagram. In your book, they have given like this, line like this. I'll not draw it like this. I'll draw it this round one. These are nothing but the d orbitals. Okay. So I'll write now here d orbitals of free metal I. So they all of them have the same energies. So what are those orbitals? dxy, dzx. Mind you, these are all these are all suffixes. Okay. So it is d yz d x. Okay, I'll write it below. Maybe it will be difficult for you to see also. What are those? Crystal fields theory is not difficult, and it takes less time than that of the valence bond theory. See here, it is dxy, dyz, dzx. Then dx, dz. So these are what? D orbitals of free metal. Let me write here now. Mn plus. Okay. Say metal ion. Don't write this one. Solution of you can any metal. Now to that, what did you do? So this is another test tube. Okay, now I'll write it here. So I'll write now here Mn plus. And to that, in a test tube, you have added, say it is this one. This is what? This is the ligand that you have. So right now here plus N ligand. In that case, what will happen? My test tube will become very small. all the ligand will now surround this metal from all sides, like this, because it's falling. In that case, what will happen? The energies of all of them, the orbital will increase, because they do not know which side it is going to come. So I'll write down here. D orbitals in spherically symmetrical crystal field. Okay. Now all ligands have surrounded. Now, the ligands are going to decide. So say I have drawn this one here, M. This is the axis. Okay. Now, ligand has two options. Whether come along the axis, this is 1, 2, 3, 4, 5, 6, along the axis, or in between the axis. If they come along the axis, they are going to meet dx square minus y square and dz square. If they come in between the axis, then they are going to meet dxy, dyz, and dzx. Let us assume that the ligands have started approaching along the axis. Let me write here. L, 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 and L. They are coming along the axis. When they come along the axis, then what will happen? The dx square minus y square and dz square orbitals will face them, because ligands are coming along with the electrons. There will be huge repulsion with there. And in that case, you will find, due to repulsion, this energy of the two orbitals will go up and others will come down. What are those orbitals which has faced repulsion? These are dx square minus y square and dz square. And which did not face any repulsion? dxy, dyz, and dzx. See, now no longer the energy is the same. That is, we say the degeneracy of the d orbital is removed. And it has led to form two sets of orbitals. Okay. I have made a little mistake. What is it? Wait, up. It should be above this. Yes, tell me.
Sir, can you please repeat that part again?
Yes, I'm going to again repeat. See, this is the metal. So, before the formation of the complexes, the energies of all the 5d orbitals are same. Because of that, I have written in same level. Then after that, I have added the ligand solution. When I have added the ligand solution, now ligand has surrounded from all sides. When it's surrounded by all sides, then you find the energy of the ligand has increased. Now after that, ligand decides which way to go and approach the metal atom. Should it see, this is the axis. It is Z, Z. This is X, this is X. This is Y, this is Y. Now ligand decides. Should it approach along the axis or in between the axis? If it comes along the axis, then this is the one. And if it comes in between the axis, then you will find, if it comes along the axis, what are the orbitals it's going to meet? These are the two orbitals are going to meet. See here, d orbital is having electron and ligand is also having pair of electron. So in that case, there will be repulsion or not? There will be repulsion. So in that case, what is going to happen? There will be a severe repulsion will be there. So to avoid the repulsion, the d orbital will be dx square minus y square and dz square will move little bit upwards. And those orbitals which did not face any energy, they will come down. So by that way, you find it generates two sets of orbitals, with difference in energy. Okay. So we have found that if it approach along the axis, then this is the splitting takes place. All right. This is the splitting takes place. So see here, this is the original energy level, and this is the splitting takes place. So this splitting is called crystal field splitting. Energy. In short form, we write here CFSE. All right. Now see. In spectroscopy, these two sets of different orbitals have a separate name. We call it T2G, and this one we call it EG. We call it T2G, and we call it EG. Now see, very interesting thing. When ligand come along the axis, what is the structure that you get? This structure is nothing but it is an octahedral complex. In octahedral complexes, the ligands always come. The ligands will always come along the axis. So what should I write now here? We'll write it here now that crystal field splitting in octahedral complexes. Okay, now see, this crystal field splitting energy here in this case, we call it delta O. Delta O is nothing but crystal field splitting energy in octahedral complexes. O stands for octahedral. Now, what is the gap between these two? You will find this is from here to here, the energy gap is 3/5 delta O, and this is 2/5 delta O. For that, you don't have to worry. See, here you have 2 on the top, so you write 2 here, and this is divided by 5. And here you have 3, just the opposite, you write 3/5 delta O. This original energy for the excited molecules, this is not being given in any of the textbook, but you should know this is called, we call it barycenter. So this is the crystal field splitting in octahedral complexes. You write it, I'll again explain to you. This gap of energy, the crystal field splitting energy, it is not being decided by the metal atom. It is being decided by the ligand. In some cases, the energy gap is very large. And in some cases, the energy gap is less. So it depends upon the crystal, depends upon the strength of the ligand. So now, the magnitude of the crystal field splitting energy depends on the nature of crystallism, even on the nature of ligands. Those ligands which generates more crystal field splitting energies are called strong field ligand. Example, carbon monoxide, cyanide, ammonia, etc. Okay. The ligands which create small crystal field will not have energy, which generates more crystal field splitting. Crystal field splitting are called weak field ligand. Example, you know, What is the example? Water.
So what's that on that moon?
Huh?
So what's that on that moon?
Which one, dear?
So on that moon?
Ammonia.
See here. The ligands which generate more crystal field splitting are called strong field ligands. Carbon monoxide, cyanide, ethane, ethylene, 1,2-diamine, ammonia, etc. The ligands which create small crystal field splitting are called weak field ligands. Okay. Example.
So shouldn't
Water.
there be energy there? Oh, no energy on the first one. Okay, sir.
No, energy I have removed. Crystal fields. The ligands which generates more crystal field splitting are called strong field ligand. Energy I have removed. The ligands which, and second one, ligands which create small crystal field splitting are called weak field ligands. Example, water. That you forgot, I think name is what? Oxalate. Then hydroxide. Then all halide, fluoride, chloride, bromide, iodide, etc. Okay, now electrochemical theory. The arrangement of ligands on increasing magnitude of crystal field splitting energy is called electrolysis. Okay. Cyanide, En, ammonia, water, oxalate, hydroxide, fluoride, chloride, bromide, iodide. Okay. Now here I'll put a break. These are strong field ligand, and these are weak field. How it happens? See, coordinate chemistry, you should get full marks. I'm going very slowly. See, now we'll go for say it is D1 complexes. Now, what is D1 complexes? Means metal is having one electron in the d orbital. So let's see. Let us go for the first series of transition metal. See here. Don't write. Scandium is what? 21. Ar is 18. 4s2 20. 3d1. But we know that if scandium 2 plus is there, don't write. Scandium 2 plus is what? 3d1. But scandium 2 plus ion does not exist. That I have already told you in your in when we discuss about the transition metals. So it does not exist. So in that case, you'll find you can never get a D1 complexes with scandium. Never. So let us rule out. Now next is titanium. Titanium is 22. So it is Ar 18, 4s2, 18 plus 2, 20, and 3d. So if you have gone for titanium 3 plus, it is what you will have here now. Titanium 3 plus will be Ar 3d1 4s0. Yes, it exists. So D1 complexes can be made by the titanium. Next come what? Vanadium. Vanadium is what? 23. So this is Ar 4s2 3d3. So if you have gone for V4 plus, in that case, what you will get now here? 4 will cross 2 from here, 2 from here. So it will be 3d1 4s. So this is also this. Okay. Similarly, if I have gone for after vanadium is what? After vanadium is chromium. So chromium, you know, if I go for chromium, it is what? It will be 4. We know. In case of chromium, it will not be 4s2. It will be 4s1, 3d5. So if I go for chromium 5 plus, in that case, you will get the 3d1. But interestingly, you know, dear, chromium 5 plus is not stable. So these are the two complexes where you find D1 complexes are there. Yeah. So now let me move. So you could understand D1 complexes. Okay. Now I'm going to show you a comparative study of the D1 complexes both by using strong field ligand and weak field ligand. Okay. So here I'm not going to draw a large diagram, small, huh? So it is this, then this, then so it is D1. See here. So D1 means what? Electron will be here. Then here the electron will go after the splitting has taken place. Okay? The splitting has taken place. You know what is we call it? We call it T2G, and this one we call it EG. Let me see whether I made mistake or not. Huh? I think I have done ulta also. Yes. In the main diagram, please correct. Huh? I always make this mistake. These three orbitals are called T2G. Huh? Sorry, dear. Hello. In the main diagram that you have drawn, please change it. Excuse me for this one. These three orbitals are T2G and other one is EG. Didi hold. Didi Rada. Duck. F-I-E-L. This one I'll draw it later on. Now I go for weak field. Okay. Now if it is a weak field ligand, what will happen? The splitting will be small. See here. Look here. This is delta O, and this is delta O. Bulu, আমি না কালকে ফুলকপি ডাটাটা সব ফাটিয়ে রাখছি তো হয়ে যাবে
এটা তখন বললে না
তোমার মনে পড়ছে আমার
তখন কি করবে
ওটার মধ্যে মূলা চলে আছে কি বেগুন বেগুন দিয়া করে দিতে হয় একটা
ও তো শালবন দিয়ে দিয়েছিলাম হবে দাদা
on this so this is this. We always know the electron always goes to the lower energy orbit. See here, it will come here. This also will come here.
কোথায় গেল দেখো ধরো এইটা
Okay. Okay. So this is what?
তুমি তো মনে করলে না তোমাকে ও আমি কুকার বের করে দিচ্ছি
Oh, ঠিক আছে. So this is wrong field ligand and this is for weak field ligand.
না আমি কুকার বের
Okay.
করতে না আজকে সংক্রান্তি না ও কুকারে
Okay, now see here. See in this
বুঝছো
case.
না এজন্য
So for D1 complexes, what will be the electronic configuration?
না করতে পারি না না একটা কথা হলো কি কুকারটা তুমি ধুয়ে আগে বসিয়ে দাও পরে কুকারটা না দিলে হলো
In this case, what is the electronic configuration? Please remember, electronic configuration of this complex is T2G1 and EG0. We write like this. Here also, the electronic configuration is electronic configuration is what? T2G EG. See, in both the cases, if you go for magnetic moment, the value will be same. We know what is the magnetic moment? Mu is equal to root over n into n plus 2 bm. In both the cases, the value of n is 1. Okay?
নষ্ট হবে না
So we can write now here strong field ligand
এটা কি নষ্ট
complex and this is for
নষ্ট না হলে তো থাকতেই পারে
sorry.
না আমি তোমাদের আমি কাটাতে তো আমি জানি না
I'll draw everything, even if it takes 2 days time also, you should know.
আমার চোখে
Please draw. These are the strong field ligand complexes, and these are the weak field ligand complexes. Okay.
তখন থেকে আমি বলেই যাচ্ছি কি রান্না করবো নিজেও
Why you know? But in your exam, say they can give you like this. Calculate the magnetic moment of hexaaqua 3+ ion using crystal field theory. It is in that case, here you have written D1 na, so here we'll write now here titanium 3+. Okay, so here we'll write here. In this case, we suppose for exam we'll write titanium, and here what we'll write now here, because we have gone for a general one, na, so you can write down here. Example is what? Titanium 3+. So you put here, it will be 1 + 2, which is √3p. You should be expert in everything. Okay, after finishing D1, dear, I will not draw. You will draw it because after this one, please draw for separately. Strong field these complexes and weak field complexes. You will draw it separately. Otherwise, I know you will not do it. Yeah.
Excuse me, sir.
Yes.
Sir, we are having a class now.
Oh,